Okay, so today we will look at the analysis technique known as node voltage analysis. Uh, if you have seen the Canvas assignments page, superposition is now due Saturday, and node voltage analysis is not due until next Tuesday. So today we will look at node voltage analysis. We will build on the concepts that we learned in last class. So let's get to the slides right there. 05. Okay. All right. So we learned about these concepts in last class, right? How to express a resistor voltage in terms of the node voltages. So we'll build on those concepts, and we'll learn about node voltage analysis. Again, on the first day of class and in the syllabus, I've specifically mentioned the first two chapters, especially. This class is built step by step by step, like brick by brick, on everything that comes before. So we learned about Ohm's law, KCL, KVL, series parallel, like how to combine resistors in series and parallel. Then we learned analysis technique, series and parallel. Now we learned about resistor voltage in terms of node voltages. We build on that using node voltage analysis. We will also apply KCL to generate our equations. So first, what we're going to do today is I will have an example illustration where I will explain the principle of NVA and how we generate equations. And then on the next slide, we will look at an example problem where we solve from the beginning of the problem to the end. So the first thing we do is identify all the nodes, select a reference node, and then assign branch currents. I will go over each step in detail. Steps 1 and 2 comprise a setup of the problem. Okay, when you as an engineer are trying to solve a problem, the first thing you need to do is to set up the problem correctly. If you don't set it up correctly, the rest of your solution is going to be incorrect. So you set up the problem correctly. A major chunk of your points will be allocated for correct setup of the problem. Okay, so correct set of the problem is very important, and I will go exactly over what you need to do to set up the problem correctly. So as an example illustration, let's draw a simple circuit. The circuit has a voltage source, and it has 4 resistors. Again, go ahead and upload your campus pass if you have not already done so, please. We call it R1, R2, R3, and R4. Okay, R1, R2, R3, R4. Okay, first things first. How many nodes do we see in the circuit? There is the bottom node, that's common, right? It's the bottom node, that's common. And then we have 3 nodes up top, right? Any place where 2 or more components come together, that's a node. So let's label this A, B, C, and D. Nodes A, B, C, and D. Okay, nodes A, B, C, and D. Then you choose a reference node. More often than not, it is very convenient to choose the ground as the reference node. But it does not have to be ground. It does not need to be ground. Okay, so it does not need to be ground. Okay, does not need to be ground. So choose D as reference node. Okay, so that's step 1. Step 2, we assign branch currents to all branches. Now, this step goes back to the point that I made in the first week of class. We assume current directions, and that assumption is up to you. but those assumptions are based on certain logic. So let's look at what logic tells us, or basically facts, if you will. Vs has plus up top, minus on the bottom. So which direction is the current for Vs flowing? It's going up, right? A voltage source is a supply, so it's supplying energy, it's supplying power. So when you supply, you're going from minus to plus. We need to put a negative sign in front of it to balance it out. So Vs will have a current that is flowing in this direction. So Vs has Is, no, sorry, Vs is supplying Is going up. R1, logical assumption is it's going from left to right, or R1, right? So for R1, we will say current IR1 is going from left to right. Following through on that assumption, we can assume IR2 is also going in that direction. Okay. And then because IR1 and IR2 are going towards the right, IR3 and IR4, we can assume is going down. Right? So IR3, we will assume is going down. IR4 also we will assume as going down. Now, important point. Setup is almost complete, right? If you choose IR2 and IR4 as going the opposite way, it does not matter. It does not matter. Your answer will be correct at the end. So you can choose, again, you can choose whatever, you can fly in the face of logic and choose the opposite direction. It does not matter as far as the solution is concerned. You will end up with the right answer. I want to keep making that same point again and again, right? Now, what else is remaining? We assign current directions. Now we need to assign voltage polarities. Voltage polarities will be based off of the current directions. So since IR1 is going from the left to the right, which end is plus and which end is minus? Left side is plus, right? Because current for passive element, receiving power, receiving energy, point of entry is always plus. Current always goes from high to low, plus to minus. So we'll mark out the voltage polarities for each resistor based on the current direction. This cannot be a illogical assumption, meaning if arrow is going from left to right, left end, it will always have to be plus. You cannot choose current going towards the right and then put a plus over here. It has to be on the left. Okay. And that completes the setup of the problem. This is what is expected of you. Actually, arrow should be the other way around. Problem setup. Because if your problem is not set up correctly, the entire solution is going to be incorrect. So this is the most important part. As an engineer in your own field, the same holds true. When you're trying to solve a problem, and somebody, if you go to an interview, they're going to ask you technical questions. They'll give you they'll give you a diagram. Say, hey, in our company, we have this piece of equipment and it does this. Now you're facing this problem. How would you solve it? So they will ask you something like this. They want to know your thought process. They want to see how you're going to solve or how you would set up that problem correctly. And so it's very important. Okay, so a major chunk of the problem grade or the points of the problem will be allocated to problem setup. So you need to identify all the nodes, clearly mark the reference node, and then assign branch currents and the voltage polarities. Now, what do the voltage polarities mean? What do they mean? All they are showing is the difference in the node voltages across the resistor, right? If IR1 is going from left to right, all it means is that point A is higher than point B. It means the voltage at A is higher than the voltage at B. Similarly, voltage at B is higher than the voltage at C, voltage at C is higher than the voltage at D. That's all it means. Yes. Yes. Yeah, always. So if the current direction was opposite, the polarity also would be opposite of what we have chosen here. Okay. All right. So as you can see at B, you can see minus, plus, and plus, right? Those are for three different voltages. It's not as if B is like minus, plus, and plus. It gets confusing for some students. That's just because it's just showing that B is lower than A, but it's higher than C and D. That's why you have a minus, plus, and plus, right? So voltage polarity is just noting the voltage or the difference between the two nodes that the resistor is connected. That's all it means. Now, once the problem setup is done, we move on to steps 3, 4, and 5. You apply KCL at each node. You apply KCL at each node, you'll have your KCL equations in the form of those branch currents. So let's apply it at, for instance, at node B. If you apply KCL at node B, I would obtain IR1 is equal to IR2 plus IR3, right? IR2 plus IR3. So IR1 is equal to IR2 plus IR3. That's what I would obtain. And that would be step number 3. Step number 4, I would apply Ohm's law and I will express each one of these currents in terms of the resistor voltages. So IR1 I can write is equal to VR1 over R1, VR2 over R2, and VR3 over R3, right? I apply Ohm's law. Step number 4, apply Ohm's law and express each current. I is V over R. So IR1 is VR1 over R1, VR2 over R2, and VR3 over R3. Make sense? We good so far? Okay. By the way, how many of you are checking the class notebook? My annotations appear all right over there? Okay. Thank you. And then finally, the 5th step, express each resistor voltage in terms of the node voltages. And then we have our set of equations. So each resistor voltage, each resistor is connected between two nodes, right? R1 is connected between A and B. Right? R1 is connected between A and B. So VR1, excuse me, VR1 is so VR1 is connected between, VR1 is VA minus VB. And here's where the voltage polarity matters, right? VR1 is the resistor voltage for R1, but it's connected between nodes A and B. And by our assumption, we are saying that point A is higher than point B. So VR1 is VA minus VB. And that's why your current direction does not matter. As long as you're consistent, you would get the exact same thing. If your IR1 was going towards the left, you would say that B is higher than A, that VR1 would be equal to VB minus VA. Does that make sense? And then it balances out when you apply KCL at the other nodes also. So here, I would write VR1 is VA minus VB over R1. VR2 is between B and C. It's VB minus VC over R2. And VR3 is VB minus VD over R3. Okay. Then at this point, you would plug in all the known values that you have. You plug in all the known values, meaning resistor values would be given to you, R1, R2, R3. Voltage source value would be given to you. You plug that in. You plug in your reference node, and you eliminate as many unknown variables as you can, and you reduce the equation down to one single linear equation. So here, let's see. R1, R2, and R3 will be given to us. Yes. Okay. So where was I? Okay. R1, R2, R3 would be given to us. So we plug in the numerical values. VD is a reference. So VD goes to 0, has gone from our equation. VA is equal to VS. So you have a numerical value here. The only unknowns left in the circuit are VB and VC. That's it. And so you reduce the equation at this point into the form of AX plus or minus BY plus or minus CZ is equal to plus or minus D. Same way you would have EX plus or minus FY plus or minus GZ to the plus or minus H, IX plus or minus JY plus or minus KZ plus or minus L. It's a set of linear equations. You can solve it with any method you choose. You solve it by hand, you solve it by determinants, Cramer's rule, matrix. You can program this entire set of equations into your programmable calculator devices. It spits out your final answers. I don't really care how you do it. This is some basic algebra, right? More often than not, you would only have like 2 unknown variables, right? So it's very easy to solve. Here, X, Y, and Z are your unknown variables. Okay, are your unknown variables. Basically, they are your node voltages. If you have one unknown node voltage, you want to have at least one equation to solve it, right? If you have 2 unknown voltages, you want 2 equations. If you have 3 unknown variables, you want at least 3 equations, and so on and so forth. Most of the circuits that you look in this class will not be more than 2 or 3. Right? Will not be more than 2 and 3. So you want to have at least as many equations as you have unknown variables. Once you have your set of equations, you solve them using any method you choose. If you choose to program it in your calculators, you make a note in there. And you solved it using a calculator, and then you simply have your final answers. VA is equal to this, VA, VB, VC is equal to this. At that point, if your answers are incorrect, the penalty is not going to be that severe. As an engineer, you should be able to program and solve this, right? So if you make an error, yeah, points will be deducted, but a majority of the points will be in the problem setup and in these equations. So I'm letting you know what is expected of you, of students, when you try to solve this. Yes. They would just be coefficients. And you will see in the next. So A, B, C, D, E, F, G, H are those would just be some coefficients. That's just showing the format of the equation. Does that make sense to everyone? Excuse me. A, B, C, D, E, F, G, H, I, J, K, L. they would all be constants. There will be some numerical value. And XYZ would be, for instance, VA, VB, VC. So it might be like 10 VA minus 5 VB plus 6 VC is equal to minus 10, something like that, just random numbers. So the A, B, C, D, those are, yeah, I get what you're saying. They're all letters, so it's confusing. I see your point now. So A, B, C, D, they are coefficients, they are the constants. X, Y, and Z are the variables, and they represent the node voltages. Okay, they represent the node voltages. Let's see. Oh, but is the procedure clear to everyone? Right? So let's look at an example problem. Here in this problem, there are a couple of reasons why I like this. It does not have any voltage source. There is a ground provided, and then you will see what the answer at the end is going to be, not what you expect. Oh, one other point. Once you have your node voltages, once you have the answer for VA, VB, so you solve the equations, you would have the answer for VA, VB, and VC, right? VA, of course, is already known. You would have the answer for VB and VC. Now, you can take those answers and you can solve for all resistor voltages, right? VR1 is VA minus VB. VA is equal to VS. You found VB, so you can find VR1, right? Or find VR2, you can find VR3, you can find VR4. Once you have those, you can find the branch currents. IR1 is VR1 over R1. And so that's how we actually solve for the resistor voltages and the resistor currents. Okay. All right. I1 and I2 are current sources. Ground is labeled at the bottom right there. We do not have to choose ground as the reference, but we'll choose that anyway. How many nodes do we see in the circuit? 2, 3, 4, 5, 6. Anyone? 3. First time I solved this many years ago, I chose like 5, or I counted 5, and I was like 20% into the problem before I realized my error. So there's only 3 nodes. There's this node right here at the bottom. We'll call it C. And all of this is one single node because it's only wires. There are no components between those wires, right? It's one single node. And this also is one single node. It's only 3 nodes. What else do we see? Between A and B, you have R2 and R3 connected, same nodes, A and B. So they are in parallel. So I'm going to combine both those together and make one single resistance, and I'm going to call that R5. Okay, I'm going to set up the problem by combining both those resistances together. So let's begin. I'm going to say this is R5, and if R5 is equal to R2 in parallel with R3, and this comes out to be 166.67 ohms or 1.667 kilo ohms. All the resistor values are given to us. The values of the current sources are also given to us. Okay. Then I have a resistor coming down here. I have another resistor coming down here. I have a current source. Okay. And this is I1, I2, R1, R4. Next step is to choose reference. I'm going to choose the bottom node C as my reference. So I'm going to call the C as my reference. reference node. A, of course, is up here, and B is around there. So far, so good. Next, we choose current directions. I1 is going up, I2 is going down. So R5, logical assumption to be made, is going from left to right. So I'm going to choose going left to right. IR5. How about R1 and R4? Not quite so clear. But again, it does not matter what we choose. We can choose them going up, we can choose them going down, mix and match, whatever you want. So for the previous two sections, what I've done is I chose both R1 and R4 going down. So let's choose it that way. Because we have I2 going down, we could potentially state I2 is 50 milliamps. It's larger than 10 milliamps, which is I1. I2 is larger than I1, so we could choose it going up. That is also a logical assumption to make. But again, it does not really matter. So if we choose it going down, I'm going to say this is IR1, IR4. And based on the current directions, I'm going to assign voltage polarities. So polarity for VR5 is going to be plus on the left, minus here. This is going to be plus minus. And that completes our setup of the problem. Right? Identify the nodes, label a reference node, assign the branch currents, and then the voltage polarities. The problem is now set up correctly. Let's go ahead and generate our equations. KCL at node A. I'm going to draw out my node. So when I draw out my node, I have IR5 leaving the node, I1 entering the node, and IR1 leaving the node. So my KCL expression, straightforward enough, I have I1 is equal to IR1 plus IR5. Easy enough, right? You proceed step by step, and then it makes chances of errors are highly reduced. The next step is to apply Ohm's law, and I can write I1 is equal to VR1 divided by R1, VR5 divided by R5. Right, good. And then after this, the final step would be to express each resistor voltage in terms of the node voltages. VR1 we chose as going from top to bottom. So VR1 is coming from node A towards node C. So A is higher than C for my assumption. And so VR1 is going to be equal to VA minus VC. Okay, VR1 is VA minus VC. And I'm going to go ahead and plug in the values at the same time. So I1 is 10 milliamps, so 0.01. VR1 is going to be VA minus VC divided by R1. R1 is 1,000. So 1,000 plus VR5 which is between VA and VB, and R5 is 166.67. Reduce the equation, and you obtain your final answer. Well, not final answer, sorry. And you obtain your equation that you want to solve. So you get 0.01 is equal to 0.0001 VA. Oh, 0.001 VA. VC is our reference point, so VC is ground, so it's sorry, not ground. VC is 0, and so that's eliminated. All we are left with is this. And that is your equation. We still need to combine. Rearrange the terms, and I get 0.0016 VA minus 0.0006 VB is equal to 0.01. That is equation 1. Equation 1. So this is now AX minus BY is equal to C. VC is our reference, so it's equal to 0. Yes. Yes. So VC is equal to, because it's a reference point, VC is 0. So it's eliminated. It's eliminated. Again, it does not have to be ground. Your reference point does not have to be ground. But when you write out the equations, the important thing to keep in mind is that your reference point, whatever that node is, will be equal to 0. Your ground does not necessarily be equal to 0. And you will see that in like the next slide, I will point it out. Because again, voltage is always measured with reference to some other point. That point can be either 0, ground, or it could be something else in the circuit. But for the purposes of that measurement, that reference point will be equal to 0. And so VC is 0 in this equation. That's gone, and we have this expression. Now, you can solve it exactly as it is, or what sometimes I like to do is, if I multiply this by 10,000, I get 16 VA minus 6 VB is equal to 100. Same thing really, but the advantage is if you're trying to program this into your calculator and you try to do 0.0016 and then 0.0006, if you forget a 0 in there somewhere, your answer is going to be incorrect. So again, just a small tip. This is why I like to do it like this. Either way, it does not really matter. Is that clear to everyone? Right? How we are obtaining. So then let's get to the other side and apply KCL at B. If you apply KCL at B, you have IR5 coming in, I2 going out, IR4 also going out. So my KCL equation is IR5 is equal to IR4 plus I2. IR4 plus I2. And then the same thing, apply Ohm's law, and I can write VR5 divided by R5 is equal to VR4 divided by R4 plus I2. Plug in all the known values. Okay, plug in all the known values and replace each resistor voltage in terms of the node voltages. VR5 still remains VA minus VB. The assumption that you make at the beginning of the problem cannot change halfway through the problem. So if you assume your current direction going left to right at the beginning, it still remains left to right. And so that means VA minus VB or VR5. You cannot change your assumption midway through your solutions. R5 is 166.67. VR4 is, what do we have? VB minus VC. And R4 is 2000. R4 is 2000. Yeah, R4 is 2000. Plus I2, which is 0.05. Again, plug in all the known values. VC is a reference, so it goes to ground. I mean, sorry, I keep saying ground. VC is a reference, so it's 0. And because it's 0, I can combine this and I can write 0.0006 VA minus 0.0006 VB is equal to, what do we have? 0.0005 VB plus 0.05. Rearrange the terms again in the standard form, and you would get 0.0006 VA minus 0.0011 or 11 VB is equal to 0.05. That is equation number 2. Or you could multiply it by 10,000 and you get 60 VA, sorry, 6 VA minus 11 VB is equal to 1, 2, 3, 4, 6, 1, 2, 3, 4, 11, 1, 2, 3, 4, 500. Yes. And now you have your two equations. AX plus or minus BY is equal to C. DX plus or minus EY is equal to F. You solve for X and Y, which is VA and VB. Any method you choose. And the answers that you would obtain should be, okay, let me scroll up. VA should be equal to, again, I don't care how you solve this. Any method you want. You solve it by hand like I do, or you use a matrix, determinants, Cramer's rule, right? Or you just program it in your calculator. If you program it in your calculator, you better be sure of your skills. You need to be able to program it correctly, spit out an answer. So you just put a note in there, solved on my calculator. Here's the final answer. VA is equal to this, VB is equal to this. So here VA is going to be minus 13.57 volts. And VB is going to be minus 52.86 volts. When we were online, I also permitted students to use like the online solver. There are websites out there where you could take these equations, just program it in there, and it'll give you the values, which is also fine with me. But you don't have a lot of surface area to actually have your laptops and everything working at the same time. Okay, so minus 13.57 and minus 52.86. What does it mean? Well, it's not incorrect as much as, yeah, it will be opposite perhaps. We don't know yet. Let's plot it out. C was a reference. VC is 0 volts. With respect to C, VA, point A, is 13.57 volts below C level. VA is right here, minus 13.57 volts. And with respect to C again, VB, again, it's obviously not to scale. It's minus 52.86 volts. That's all it means. Doesn't mean anything else. So these results for node voltages are solely for reference node being at C. If you choose your reference node to be at A, you choose your reference node to be at A, then VB and VC are your unknowns, right? If your reference is at A, then VC, what the? Okay, then VC is going to be plus 13.57 volts. And VB would be equal to, what do we get? 39.29. It'd still be minus because B is still lower than A. So minus 39.29 volts. And then one more point to illustrate is if your reference is at B, reference is B, then VA would be equal to plus 39.29 volts and VC would be plus 52.86 volts. Okay, that's all the numbers mean. And that is the reason why if your assumption, if your reference node is different from someone else, your node voltages would be different. These, I mean, you can see there are some similarities in the numbers, right? Because the voltage levels are not going to change. The levels that you see in this diagram, A, B, and C right here, they are not going to change. They will remain the same. But it's the way that you find it that would be different. From here, you have VA, VB, and VC. Whether you take this, this, or this as your reference, your resistor voltages will not be different. You can try it out. You can take these numbers where VC is 0, this is minus 13, this is minus 52, and you calculate all your resistor voltages. Then reference is A. So VA is equal to 0, VC is plus 13, VB is minus 39. Calculate the resistor voltages. Do the same with this one. All three of them should give you the exact same resistor voltage. That will not change. And that is the point of the technique. It doesn't matter what assumption you make, the resistor voltages and the resistor currents will always be correct at the end. Doesn't matter what reference node you choose, doesn't matter what current direction you choose, as long as you're consistent within the problem, meaning you don't change your assumptions halfway through the solution, your answer will always be correct. That will not change. So it's also important to understand this diagram because it shows you exactly what it means. VC is 0, minus 13.57 just means A is that many volts below C, and B is minus 52.86 below C. That's all it means. All right, questions? Any questions? Does the method make sense? The application of the steps, your expectation or my expectations from you. Is everyone clear on that, on what you need to do to get your correct or full allotment of points, right? No, no, that's just for students' understanding, just to, and that's why I particularly like this problem. It does not have a voltage source, and the answers at the end are like negative. So then students are always, not now, but in the years past, they would always have questions. And so, I learned to draw that diagram because it makes a lot more sense. Visual representation makes it easier. One last point is about supernodes. It sounds like a fantastical concept from like a Marvel movie, but it's not. It's actually very simple, very straightforward. What do you do if you have one voltage source in your circuit? You choose one end of the voltage source as your reference point, right? So let's say we just had the 10 volt source in there. We choose V1 as our reference, and V2 would be plus 10 volts. Easy enough. If we choose V3 as our reference node, then this ground would be plus 15 volts. Again, do not get confused. Our ground would be plus 15 volts. But in this illustration, this point, let me write, instead of saying this and that point, let's write this out as, well, node 1, node 2, node 3, and node 4. And node 4 is our reference node, right? So if node 4 is my reference node, it's also ground, but actually ground does not matter. The voltage source is connected with a plus at my reference node and minus at 3. So if your voltage source is a plus here and a minus here, automatically it means this end 3 is lower than node 4 by 15 volts. And that's why V3 is minus 15 volts, right? So we eliminated 2 nodes. Node 4 is 0, node 3 is minus 15. The only 2 unknowns left in the circuit are nodes 1 and nodes 2, the V1 and V2. But there is a voltage source connected between V1 and V2, right? So if there's a voltage source, if I say there is current Ix flowing to the voltage source, we cannot represent Ix using Ohm's law, right? Obvious problem. Every other current I can write. IR2, I can write as VR2 divided by R2. Can do the same for R1, R3, and R4. I cannot do the same for Ix. So what should we do? We want to eliminate Ix from our equation. We want to eliminate Ix from our equation. So what we'll do is we'll apply KCL at either end of the voltage source. We apply KCL at either end of the voltage source. So if I apply KCL here, I can write Ix is equal to this current IR2 plus IR1. That makes sense, right? Doesn't matter what direction the currents are going, but I can rearrange the expression to say Ix is equal to IR2 plus some combination of IR1. Make sense to everyone? Then at the other end of the source, node 2, I can again apply KCL. I get another expression for Ix. Ix would be IR4 plus IR3. Ix is now equal to A. Ix is also equal to B. What can I say about A and B? A is equal to B. Ix is gone from my equation. And that's what the supernode allows us to do. When you have more than one voltage source in a circuit, whether you have 2 or 3 or 4, you take one source, you choose one end of one source as a reference. That's done. For all the other voltage sources, you create a supernode. The supernode simply means you're taking that voltage source and you're shorting it out. You're combining this node and this node together to form one single node. And then you apply your KCL directly. So if I do that, I have one single node, IR2, IR1, IR3, IR4. I can directly write IR2 plus IR1 is equal to IR3 plus IR4. No mention of Ix anywhere. But you can try this out for yourselves. You apply KCL at node 1 and KCL at node 2. You can get Ix is equal to IR2 plus IR1 and Ix is equal to IR3 plus IR4. Then you just equate both of them together and you have your supernode equation. That's all it means. Yes. Just one. Just one. Okay, quiz on Monday. The quiz on Monday will not include node voltage analysis. Everything else before node voltage analysis is fair game. I will send an email with the details. I will be available all weekend via Zoom. I'm also available in my office later today if you need to see me. I'm also available via Zoom today also. Superposition homework is due Saturday. Check your Canvas calendars. And then node voltage analysis is due next Tuesday. Have a good weekend, and I will see you all on Monday.